part 4 of lesson 2.7, circular motion. So this is a practice problem number 1. Base your answers to the following questions on the information and diagram below. In an experiment, a rubber stopper is attached to one end of a string that is passed through a plastic tube before weights are added to the other end. The stopper is whirled in a horizontal circular path at constant speed, right? So look at the diagram. On the diagram below, draw the path of the rubber stopper if the string, breaks at the position shown, okay? So this is kind of what you guys did in the lab activity, essentially. So if the string breaks, right? So they say draw the path of the rubber stopper if the spring breaks. Sorry, I keep saying spring by accident. Okay, so this is the position. Remember, velocity is tangential, okay? So that is actually what it would look like, okay? You don't have to draw, for example, you don't have to draw on the whole line. You don't have to be like, oh, that's what it would look like. We know that the object is moving counterclockwise as showed by the arrows. So it's just okay for you to draw just one end of the arrow of the line from that position. So this is what it would look like. Remember, velocity is always tangential. That's just another way to say, you're just taking the tangent, right? So remember, you're just crossing that curved point with a line. And this is why I was so adamant about it in lab, because I knew that if that rope broke while you guys were swinging it around, I knew that someone who was standing next to you, velocity's tangent was going to get hit in the face, and that's why that was a big concern there. So let's move on to practice problem number 2. In the diagram shown, satellite S moves in a circular orbit around Earth. Okay, the direction of the acceleration of the satellite is towards point which one, right? So that's what they want us to figure out. Remember, centripetal acceleration always points inwards, okay? So with that being said, there should be one clear answer here. So if you are looking at the examples, which honestly I just noticed this now, I think this little A was supposed to be a capital B. But anyway, so we clearly see that B, C, and D are outside of the circular path. And we know that centripetal acceleration points inwards, right? So the only choice that would make sense would be choice A. Okay, the other ones are all wrong. They're outside the path. Okay. In the diagram here represents a mass of 1 kilogram traveling at 8 meters per second in a circular path of radius 4 meters. If the mass of the object is doubled, the magnitude of the centripetal force will be what? So they want to know if you change this mass, what will it actually change by? So kind of similar to what we used to do in the gravitational attraction lesson, okay? I have a mass of 1 kilogram traveling at 8 meters per second in a circular path. My radius is 4. We know that Fc equals mv squared over r. Remember, that's my combined formula. So if I do these together, I would get Fc equals, the mass is 1 kilogram, 1 kg times 8 meters per second. You square this, and then you do 4 meters, okay? What you should get here is 64 divided by 4, that's 16. If you do part 2, where you actually double the mass now, again, you're going to plug everything in, so you're doubling the mass, so it would be 2 kgs instead of 1. It's still going to be 8 meters per second squared over 4 meters. You'd actually get it to be 32. So if you do 32 divided by 16, that's actually changed by 2, so it's twice as much. Okay, here we have a 7 kilogram hammer. It's in a horizontal circle. It has a constant speed of 12 meters per second. The radius is 2. We're looking for the magnitude of the centripetal acceleration. So list our givens. We have V equals 12 meters per second. M is 7 kilograms. And the radius is 2 meters. Our unknown is AC. We don't know what that is. Our equation is AC equals V squared over R. We substitute with units. AC equals 12 meters per second squared over 2 meters. So that's 144. So we get AC equals the following. 72 meters per second squared. Okay. And then finally, our last question. We have a 12 kilogram car is traveling at a constant speed of 9 meters per second squared. Sorry. And it's traveling in a circular path of radius 25 meters per second. The magnitude of the centripetal force acting on the car, that's what they want us to figure out. We do our givens. Our speed is 9 meters per second. I'm so sorry for my dogs in the background. 12 kilograms. And our R is 25 meters. Our unknown is FC. That's what we want to figure out. The equation we would use would be mv squared over r. Okay, so now we're going to substitute. FC equals 1,200 kilograms times 9 meters per second squared over 25 meters. If you were to solve that, you would get the following value, which is 3,888 newtons. And if you put this into scientific notation, you get 3.8 times 10 to the 3 newtons. The closest answer that would make sense is 3.9 newtons. 3.9 times 10 to the 3 newtons. Okay, right? So it rounds up into that. And our last question. So on a flat horizontal road, right, it's 1,500 kilogram car traveling around a curved road that has a constant radius of 45 meters. The centripetal acceleration is 3.2 meters per second squared. They want to know the car's speed as it travels around the curve. So let's label our givens and unknowns. 1,500 kilograms. R is 45 meters. And then we know my centripetal acceleration is 3.2 meters per second squared. Our unknowns is the velocity. The formula we would use is AC equals V squared over R. We're simply going to substitute. Okay, so actually let me erase this. My AC is 3.2 meters per second squared equals V squared over 45 meters. You're going to cross multiply here. The value that you get is 144 equals V squared. In order for you to get rid of this square, you have to square root on both sides. Then you would say your solution part. You would say the velocity is 12 meters per second. Okay, so the questions are pretty simplistic. You just have to know what variables you're being given, and then just have to figure out which formula would be the most appropriate to plug in.